You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Edward Schmidt. Dr. Schmidt is a Professor Emeritus at the University of Nebraska-Lincoln, having taught physics and astronomy for over 40 years. He has well over 50 peer-reviewed articles, mostly focusing on variable stars in professional journals, including the Astrophysical Journal, the monthly notices of the Royal Astronomical Society, and Astronomy and Astrophysics. His most recent paper looked for analogues of Tabby Star using previously available survey data.
One of the most gratifying things I read in the comments is how this show and my channel helps people to relax and sleep. That is why I'm happy to share that this episode of Event Horizon is brought to you by Endel. Endel is an app that creates personalized soundscapes to help you relax, focus, and fall asleep. If you have trouble sleeping, feeling tired, and that your sleep quality is not good enough, Endel can help soothe you into a deep sleep with soft, gentle sounds. Indeed, the scientifically engineered sounds are there to help mask or cover distracting noises in your sleeping environment, as you can let the colored noise and nature sounds help you to drift smoothly to sleep. Endel's patented core technology, Endel Pacific, adapts in real time to personal inputs like location, weather, and your heart rate. I encourage you to check out Endel by clicking the link in the description. The first 100 people to download Endel will get a free week of audio experiences. Thank you to Endel for sponsoring today's video. Professor Edward Schmidt, welcome back to the program.
Thank you.
Now, Professor, for a number of years now, since 2015, as I recall, we've had this strange case of a dipping star, KIC 8462852, or a Boyajian star. And you have spent some time now, over 2 papers, looking for like examples so that we have something to compare this dipping star to. And you've had some success. Now, have you found anything that's, effectively identical? Or are these just sort of in the similar class, behaving similarly, but not exactly?
Well, in terms of the stars that I found, they all occupy a restricted range of temperatures and a restricted range of brightness or luminosities, which is statistically significant. And if I just had pulled stars at random out of the survey, the chances of getting them clustered as well as they are would be like 1 in 10,000. So statistically, they seem to be very close to each other in terms of their main properties of temperature and luminosity. And Boyajian star falls right into that group very nicely. So it does appear that I've narrowed down the type of stars that are doing this.
These types of stars, as I recall, Boyajian star is a type F.
Yes.
Are these all in that similar grain on the diagram?
Yeah, they range from early F to, well, roughly late G. So the sun would be in that same range. And then in terms of their brightnesses, Boyajian star is a dwarf or a main sequence star, and most of these are, but there's also some which are brighter and would be faint giants or subgiants or something like that. So there's a range there, but again, it's restricted because, of course, they're really giants or supergiants.
Does this phenomenon, looking at a sampling of them, does this really look like some new phenomenon of dust in orbit of these stars, or is this still quite open?
I think it's still open. I think the case for dust is reasonably strong because of the color dependence of the dips that were observed several years ago. They have the right kind of color change when they dip, so that's consistent. So, and of course, we don't have that same kind of information for the 30 stars I've found, and that's something I'd like to get. But of course, it's hard to do because they dip when they want to, and you can't wait. You can't predict. So anyway, I think that's the leading idea now is that the actual absorption that causes a dip is due to dust passing in front of the star.
Do you have any hope for amateur help here? Because I know with Boyajian star, there's a number of variable star observers that have really nice photometry equipment that are on an amateur basis doing citizen science to monitor it. Is there any hope here to have AVSO or one of the variable star observers take a look at some of these stars as candidates and see what they're doing long term?
Yeah, I would think that's a good idea, and that's something that I want to pursue. I haven't pursued it yet. I've been busy getting what I could together about them. That is something that I'd like to see. One of the problems, of course, is that from the observing perspective, this dipping occurs, at intervals on Boyajian star several years, and the stars in my group, just as a rough estimate based on looking how they behave, it seems to be similar several years between the dipping events, and so it's not as exciting as observing something that really changes, in a few days or months or something. But nonetheless, I think that the science that can come out of them is certainly worth the effort.
Now, infrared has been a problem with Boyajian star in that we don't really see any with the instrumentation that was used. Do you think it would be of value to take a look in infrared at some of these other candidates to sort of characterize what this dust, if that's indeed what it is, what this dust is doing and what its origin is?
Yeah, right. That will be the next step, and so that's one of the things I've got on my list to do next, is to go through the literature and find whatever infrared observations I can, and then look to see if there's any kind of an excess that could be dust. So that's certainly another step, a next step.
The one thing that seems to stand apart here, though, is that these are also SETI candidates because there does appear to be a clustering of them that doesn't appear readily explainable, correct?
That is true, yeah. That is a clustering. It's not a very large cluster. There's 8 stars in it, plus Boyajian star falls right into it too. So this is in an area centered on the constellation Lyra. I first noticed it when I plotted all these 30 stars on the sky to see if there was any kind of distribution, and there was an obvious clump to the eye, and of course it's right next to the plane of the Milky Way, so I had to check and make sure it wasn't just that there's a lot of stars there anyway. But it turns out that's not the case, that there really is an excess compared to the number of stars in the field. So, and then I went on to use the data from the Gaia mission, which has parallaxes, and so I could get distances of all of them. And when I did that and then looked at their distribution in 3 dimensions, lo and behold, of those dozens or so stars in the clump, there were 8 that were clustered in distance as well, so that they did really form a clump. And then Boyajian star, again, is contained in that. So that's it's very hard to explain because, of course, the way I found these stars was to look at this survey that had no data whatever except for their brightnesses of all the stars in their catalog, and there was no color data, nothing like that. So they were selected without any information about these stars aside from how they behaved in time with regard to their brightness. So finally get to the end, and there's a definite clump. That's really surprising. And it's hard to know quite how to explain it. And as you mentioned, SETI is one obvious thing that one thinks of.
People are going to ask, what about the idea of obscuring material in the interstellar medium? But wouldn't you see that around all stars in that region, if that were the case?
Well, yes. And of course, that has been suggested for Boyajian star. And you might say, well, one star, maybe there's something really peculiar in the dust distribution. But when there's a number of them and they're scattered around a big area where there's many, many other stars that aren't doing anything like that, then I think that pretty much rules that out.
Now these stars also probably aren't originally related, right? So they're probably all from all over the galaxy and have just been moving around through proper motion. And this clustering gets even more mysterious then if you take that into account, right?
Yeah.
Because you can't really blame it on material that's inherently around these stars from the beginning.
Yeah, I think that's right. And one of the other things that should be done, and that, again, on my list, is to look at their motions and see if we can get any kind of sense that there's anything in common in terms of their motion. There are large groups of stars that are fairly scattered that have common motion, and this is because they were a cluster which grew and expanded until the stars were quite far apart, but nonetheless they retained that common motion. And so looking for common motion would be something to do, but I'll be very surprised if it turns out that that's the case.
And even if you did find some commonality, you still have to explain why this particular group of stars has this weird dust juxtaposition and nothing else does. You don't seem to see it very many other places.
Yeah, right. So it doesn't help.
Right. Well, anybody that's interested in this star, KSE 8462852, is used to the mystery deepening at this point, because that's just when you think you got something. Nope.
Yeah, exactly. It seems like it's gotten more mysterious rather than less.
Now, Professor, say a SETI search. What would they look for? I mean, obviously, they'd look for radio emissions, but what about laser and things like that? Are these suitable stars to look for with that type of thing in mind?
Yeah, certainly. And one would hope that SETI people would find this interesting enough to do both radio searches and optical searches. And that was done for Boyajian star. Both of those were done. And of course, didn't yield anything. I would say, though, one of the problems with this is that if they do that and find nothing, that, of course, doesn't mean there's not intelligent life there. It just means they're not sending us signals right now. So it's one of these things, if you found it, it'd be great. If you don't find it, it doesn't tell you a great deal.
And it has to be remembered that we're talking about some pretty distant stars here. I think Boyajian star was over 1,500 light years distant, right?
Right. So the closest one in this group is about 680 light years away. And then the most distant one is more like 1,600. So they're spread over quite an area, or quite a region of the galaxy.
That makes SETI harder because of the distance, and if you're looking for a weak radio signal, it gets harder.
That is true, yeah, exactly.
What is your next step on trying to determine what these stars are doing? Is it just look for more, or is it try and push ahead and get deeper observations of these stars?
Yeah, I think the next steps are, well, we've already mentioned a couple. One is to go back to all the infrared studies that have been done and see if we can find anything that, in terms of the excess emission in the red. Then I intend to go through the other surveys and confirm that they're doing some of this in other surveys as well. And also, if we had more data by looking through other surveys, we might be able to find things like some periodicity. I understand that some people have found some pretty good evidence of periodicity, or at least of something repeating in Boyajian stars. So this would be another interesting thing to probe. But then more observations are always what we need, of course, for everything.
Indeed. But this, if you see periodicity, though, that constrains things, because then you know it's in orbit of the star, right?
Yeah, exactly. That would be a very good clue.
Now, specifically moving towards type G, which is getting into very sun-like territory. So even stars like the sun could exhibit this. Now, do we have anything in the solar system even closely analogous to this?
No, I don't think so. Comets kind of share some of these properties, because when they get close enough to the sun that they begin to sublimate the ices, and then they also have dust in them that gets spread out. But they aren't big enough, they don't have enough material to really do much to the sun in terms of its brightness. So one could imagine maybe a comet that had a much bigger, more massive nucleus that could produce a lot more dust and gas, and maybe that could play a role. But that's a far stretch from the kind of comets we know about.
As I recalled, someone had a paper, I think about a year after the announcement of it, that seemed to shed some light on that comets would be on this level, on the level of Boyajian star, would be implausible, because you just need so many of them. But at the same time, I mean, you have to have a mechanism. So what about collisional models? Do you think things like, I don't know, evaporating moons or colliding asteroids or things like that might be a decent direction to move as far as figuring this out? Yeah,
the problem is that if these dips really do repeat, as like I said, there's some indication of that, then there needs to be a pretty continuous source of the dust, and collisions will produce a lot of that kind of thing, but then it'll all dissipate. So I haven't quite thought up a way that would work. I was rather thinking maybe a model in which there was a large object, like a comet nucleus, but much, much bigger, that was in an elliptical orbit. It might get in close to the sun and emit this dust and provide some of this. But whether or not that's it or not, this is all very speculative.
The dust in regards to Boyajian star is very fine.
Yes.
Very tiny dust. And as you mentioned before, when you look at it in different wavelengths of light, you can see the difference in this that tells you it screams dust. So that seems to be another thing to look for with these candidates, is to see if you see the similar type of difference between red and blue, and then try to figure out if this dust is the same size basically as Boyajian star, then that would go a pretty far way in saying, well, we have a phenomena that's shared here, right?
Yeah, I think so. But one caveat would be that the dust size, that my recollection of in that first paper, they did some calculations of what kind of dust they'd need. Well, not the first paper, but the paper after the second set of dips. And I'm thinking they were talking about micron sized dust. And that's pretty much what gives us the interstellar reddening. So the interstellar dust contains a lot of particles that are in that same size range. So it's not uncommon or unheard of.
Tiny dust, but you still need a mechanism, because that would seem to me to be something that would be blown out of a star system pretty quickly. So you'd need something generating it pretty regularly within a star system, right?
That's right. You need a continuous source. And of course, another question we might ask is whether this is a transient phenomenon. Maybe it'll get blown away, and then Boyajian star won't be any different from any other. So that's another possibility. But it needs a source for a while anyway.
Yeah, as far as, there are people that have said that looking back at photographic plates back into the 30s, there appears to be dips from this thing.
It seems to have been going on, yeah.
And then there's also the question of the overall dimming trend, long term, which again, the plates seem to show that this system is progressively dimming as a whole. So I guess you don't just have a situation where it's being replenished, but it's being replenished faster than it's being blown out, which is hard to envision.
Yeah, and I don't have any real good feeling for what causes the long-term dimming, although there was one paper that I think maybe 3 years ago, which claimed that looking at some survey data, they would see that Boyajian star had dimmed for a bit, several years, whatever the times were, and then there'd be a uptick in the brightness, and it would get back to where it was and start again. Because, of course, if it continually dims at the rate that's been measured, it'll be gone in what isn't a real long time span for stars.
Yeah, and stars tend not to just disappear.
No, there's not many of those. There is a program in Europe where somebody's trying to find stars that have disappeared, but as far as I know, they haven't actually found one yet, so...
Nothing conclusive. She's been on the program, and worth a look, though. The idea of transient things in the sky is pretty amazing, considering when I first got into amateur astronomy 35 years ago, the sky was almost static, other than Jupiter getting hit by a comet or something like that. Rare events, but now we see things in almost real time, and it's only getting better.
Right. Yeah, the instrumentation now is such that we almost see more than we can handle.
Yeah, well, sometimes we do. Just think about the SETI people having to dig through, with computer programs, all of the signals that they, frivolous signals that they get, and interference, and, the radio of the cosmos itself, and just trying to weed through all of that. You can only do it with a computer because there's just so much data.
Yeah, exactly. And then when the Rubin telescope comes online, that'll produce an enormous amount more. So.
Yeah, but that's going to be exciting, because that's, whether it's asteroids or weird objects, interstellar objects, things like that, that instrument is really going to shed a lot of light on that stuff. But will it shed light on these dipping stars as well?
Yeah, and that I don't know. assuming that we'll probably be able to find more of them in the data that comes from Rubin, for sure. But one of the problems is that these are all going to be pretty faint stars. That it's designed to go down to very, very faint levels, especially over time. And these may be stars that are interesting, but too faint to really do a lot with. And as you mentioned, if we want to do SETI, we're limited in the distance just by what kind of radio waves we can detect, what fluxes we can detect. So I'm not sure how much it'll help this project or this question.
Now, another natural question and extension of that is, how about TESS? Is TESS proving to be something that could be used, or are the stars just too distant for that experiment?
Yeah, these stars are too faint for TESS. And as far as I know, TESS hasn't found any similar behavior, but this is really a rare event, because in the Kepler field, out of 150,000 stars, Boyajian star appears to be unique, and the kind of numbers I have are that maybe 10 stars in a million in the fields I've looked at with the old survey are doing this. And so basically, it's a pretty rare event, and TESS is not observing enough stars to expect to find really rare events. But I could be wrong. They might find something like that.
But that deepens the mystery, because if you see clustering among very rare stars, that's sort of a red flag, right?
Yeah, exactly. That's really hard to figure out. I should say that the statistics of this clumping are not real strong, because there's only 8 stars plus a Boyajian star, so 9 stars, and the chances of seeing a clump just on the sky like this presents itself as is only the chance of that being just from random statistics is about 7%. So that's not considered a real high statistical test, but it's enough to suggest something very interesting that should be followed up.
Yeah, that's more puzzling behavior by these weird stars. I'm personally hoping that infrared sheds light on it, because if you see infrared, then you can comfortably say, well, this is dust doing something that dust does, as opposed to just the weird Boyajian star measurement where there just wasn't any infrared. Now, the other thing is getting outside of these sort of sun-like stars, F and G type stars. Do you think the phenomena has a chance to be seen with anything else? I mean, could we see this with a red dwarf, for example, or even a giant star, for that matter? Because I remember, Betelgeuse last year decided to dim on us, but it was a completely different mechanism.
Yeah.
So could this go beyond those two classes?
I would say it doesn't seem likely, simply because the ones I discovered were all, in the same F and G range and up to subgiants and between main sequence stars and subgiants. So the fact that the survey I used to find these was, covered just a random sample of every kind of star, and we didn't see them outside this region, suggests to me that probably not.
And I guess there could be stellar dynamics involved, where if you have a giant star, it's kind of hard to keep dust around it as opposed to a smaller star, I suppose, right?
Yeah, and those kind of things may come into play, too.
All right, Doctor. Thanks for checking in with us. I wish you good luck with your work. And as soon as more observations come in, let me know, and we'll have you back and talk about it, because I'm fascinated by these weird stars. But then again, the universe is still full of mysteries.
Thank you for having me.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.